Okay, so what I'm going to take a look at right now is a new type of function, and these functions are called piecewise functions. And interestingly enough, you've already done a lot of work with them, and you just haven't realized it yet. And so we're going to start to take a slightly bigger exploration into them. The idea behind a piecewise function is simply this. One equation or one function is not enough to define the whole thing. So they are made up of pieces of functions. So for example, I want you to consider the following story. We've got time on the x-axis. That's a pretty common x-axis label right there. And then on the vertical axis or y-axis, I have distance from home. So say the story goes like this. I leave my apartment and I go for a run. And I'm going for a run and I keep a pretty steady pace, and then I end up as far away from my home as I'm going to get. And when I get there, I was headed to a park. And I spend some time hanging out the park. I watch some birds singing. I don't know, watch a dog run around. Excuse me. I spend some time at that park, in which case my distance from home stays the same. And then I look at my watch and realize I'm running late, and I got to sprint back home nice and quick so that I end up back home. As you can see in this story, there are three parts. There's my initial jog going away from home. There's the time I stayed steady spent at the park. And then there's a time where I ran quickly back home because I needed to get back. There's three separate pieces. All a piecewise function does is it says, guess what? I can't write one equation that fits everything. But I can write an equation for the first part, and I can tell you where it's true. I can write an equation for the second part, and I can tell you where it's true. And then I can write an equation for the third part, and again, I can tell you where is it true. And so that's what we're going to take a look at right now. So I'm going to jump to another worksheet. I'm going to post this on the website if you want to take a look at it. And let's just streamline this a little bit. Okay. I'm actually going to jump to number 2 because I don't want to deal with the absolute value part just yet. So we're going to jump to number 2 for a second. Nice clean problem right there. Let's see if I can zoom in a little bit so that we can see. Okay. So this problem right here is going to take us through the parts that we need. It's going to take us through the graphing piece. It's also going to take us through the evaluating piece, which I'm going to show you 2 different ways. Essentially, what you have with a piecewise function is you have each function or equation. So in this case, we've got 3 separate parts. And for each part, we are given a domain restriction, or a set of values on the x-axis where it's true. So I'm going to start right here, negative x. Negative x is a line. If I want to graph that line, I have a y-intercept starting at 0, and I'm going down 1 over 1 for my slope. So I could come over here, and if I grabbed an ID card or a straight edge, I could graph in the entire line for y equals negative x. This line right here is the line negative x. However, my domain restriction says, guess what? I only want to exist from negative 4 to negative 2. Okay, so what that means is if I come over here to negative 4, that's where my graph starts. And if I go until negative 2, that's where my graph ends. So in reality, my graph for that y equals negative x portion is only this little piece in yellow. It's not the rest of that line. The rest of that line is not parts of the function that I want. I only want the part in yellow. Now, technically speaking, the only other detail we got to take care of is these pesky little inequalities. So I want to remind you that when we have inequalities, if we have the or equal to portion in them, they're going to get a closed endpoint. And if they are simply a less than or greater than, they're going to get an open endpoint. So for the case of this first problem, at -4, I should have a closed dot. And at -2, I should have an open circle. So this is going to be a little hard to see. I need to try and write a little bigger, I realize that. But I've got an open circle here at -2, but I've got a closed dot at -4. And this portion right here is my graph, y equals -x, but only for these values on the x-axis. I'm going to go ahead and jump to the other part. And I'm going to see if I can pull it off. So I've got x minus 3. So that means I need to start down here at -3. And I've got a positive slope of x. Okay? So I can come over here again with my straight edge. And I'm going to imagine as best I can. I feel like I'm off. Okay, there we go. So there's that line, y equals x minus 3. And now I've got an interval going from -2 to 1. So if my line is going from -2 to 1, here's -2. That's where that line starts. And that line is going to go all the way to a positive 1. So if I find positive 1, I go to where my line is. Now, no bar underneath, so that's an open circle. And I need to connect those two dots. So that second equation, I only want that piece in red. And then I'm going to do one more section. I've got x squared minus 2. To get x squared minus 2, personally, I'm just going to plug in a few points. So I know I need to start at 1. So to start at 1, you plug 1 in. Okay. If I plug 1 in to x squared, I'm going to have 1 minus 2, that's a -1. So this graph is going to start right there. Closed dot because I've got the bar underneath. I'm going to plug in 2. 4 minus 2 is 2, so I go up here to 2. I plug in 3. 9 minus 2 is 7, so I'm up here at 7. And I've got my curve opening something like so. I've got an arrow to the end of my green graph because there is no barrier. So, just to recap, for each of these equations, I imagine drawing the whole equation, and all the interval does is change where that graph exists. So rather than it existing everywhere, because a line should go for all real numbers, right? Everywhere in the negative direction, everywhere in the positive direction. I instead sandwich or limit what values work. In addition, if your graphs have bars underneath, they are or equal to inequalities, they get a closed dot. And if there is no bar underneath, they get an open circle. The end result, if you might pay attention, this one had an open circle, and this one had a closed dot. This one had an open circle, and this one had a closed dot. If you had two closed dots on top of each other, you would no longer be a function. The point of a piecewise is you should still remain a function, and that's what these graphs are trying to do. So, now that we've sketched our graph, I'm going to jump down here to evaluating. If you have the graph, it works very, very nicely. You take the value of the point you're looking at, -4, you go up, you read the point on your graph. You plug in -4, you get 4 as the output, you would be able to say your output is 4. Another option you have to find these values is to use your equation up here. So for example, if I ask to find -2, what I should do is if I look at my inequalities, I need to see which one is -2 true for. If I try to plug -2 into the top equation, or top inequality, sorry, -2 less than -2 is not a true statement, so that would not work. If I try to plug it into the bottom one, -2 is greater than +1, that also doesn't work. Negative 2 is only true as an input for this middle inequality. Negative 2 greater than or equal to negative 2. So that would mean I could plug it into this equation right here. X minus 3, I would have negative 2 minus 3, which equals negative 5. And then finally 1. I can plug in 1 right here. 1 is greater than or equal to 1. That is true, so plug it in. 1 squared is 1, minus 2 is a negative 1. I'm going to plug in one more value just for the sake of example. Suppose I came down here and I asked you for f of negative 10. Now, from our graph, obviously if I plug in negative 10, I have nowhere to go. My graph stops over here at yellow. There is nothing over here at negative 10. If I also looked at my inequalities, you can also see that I have nowhere to go. Negative 10 isn't greater than negative 4, so that's false. Negative 10 isn't greater than negative 2, that's false. Negative 10 greater than 1, that's false. So in the case that your value has nowhere to go on your piecewise function, it simply does not exist. There is no solution for which you are interested in finding. The only other thing I'm going to touch on, because I think it gets mentioned in one of the problems at one point, is domain and range. Remember that domain is your x values, and range is your y values. So with that in mind, if we looked at this particular graph at the left, if I think about all the x values that will be parts of my solution, so anything that exists on the colored ordered pairs, then right now my graph is starting on the left-hand side at negative 4 and is continuing on the right-hand side by hitting an arrow. So what that means is when I look at the x-axis values, I can include anything from negative 4 up to, anytime we hit an arrow and it keeps going on forever, we think about it as infinity. In this way, I would be able to say that my x-axis or domain values are going to be negative 4 is less than or equal to x. Now, had this right-hand side been a number or an endpoint rather than an arrow, it might have changed. Had this ordered pair over here been an open circle instead of a closed dot, then I would not have included the equal to under my inequality. I can do the same thing for range, but now I'm looking at y values. So the idea behind the y values is I want to sandwich bottom to top. So my bottom boundary limit is going to be down here at negative 5. And my top boundary limit, same as before, is going to be hitting an arrow. However, there's an extra little gap right here. And that extra little gap is right in this space. Because technically, do any of my functions give me an output between negative 1 and negative 2? No. I need to show that in my range. I need to show that those values in that space is not possible. So I'm going to write one interval for the red function. That red function is negative 5 less than or equal to y less than negative 2. Notice I did not include the bar underneath in my inequality because I have an open circle there at 2. I'm now going to write a second inequality for my green function, which does include the values for my yellow function, so I can just think about doing the green one right now. And I am running out a little bit of space because I didn't plan this out super well, so I'm going to try and fit it underneath. I have negative 1 less than or equal to y, and that should suffice because this boundary goes up to infinity because there is an arrow at the top. Had I had a different boundary, I would have included another number on my inequality. That is a very small taste of piecewise functions. I will post more, but I just wanted to get you started with that.